Assalamualaikum warahmatullahi wabarakatuh and good day to everyone. In this video, I would like to discuss about the first chapter in numerical method, that is about introduction to numerical methods. These are the contents of this video. So I will start with what are numerical methods, and then we go to the explanation about errors, and then we go to the explanation about Taylor expansion series, then truncation error, a run-off error, and last but not least, total numerical error. In this chapter, there are 4 objectives. The first one, everybody must know how to introduce the concept of precision and accuracy. Second objective, you must know how to compute the approximate and also the true percent relative errors. The next one, know how to approximate the function by using Taylor series expansion. And the last objective, everybody must know how to define the concept of run-off error, truncation error, and also total numerical error. Okay, so now let's go to the introduction of numerical methods. So what is a numerical method? Numerical method is an approximate method to solve many real problems, many mathematical problems, where the solution that you will get approximate solution. Okay, what is an approximate solution? Approximate solution is a solution that close to our true solution. Okay, for numerical method, it can solve many kind of problems such as nonlinearities, complex geometries, and many problems that hard to solve analytically. And the best thing about numerical methods, it can implemented directly on digital computers. So now this is the explanation about errors. Okay, so what is errors? In numerical method, errors always occur during the computational process. And how to measure the error? Okay, we measure how close the approximate solution that we get with the true value. Okay, in errors, we can characterize it by 2 types of measurement. The first one is accuracy, and the second one is a precision. So what is an accuracy? Accuracy is how close the computed or measured value to the true value, while precision is how close a computed value to previously computed value. So for better understanding, so this is the figure that will tell you about accuracy and precision. Okay, so we go to the first picture. Okay, first picture is about accurate and precise. Why this one is accurate? Because all the 4 bullets here, close to our target. And this is precise also. Why precise? Because all the 4 bullets is close to each other. Okay, so, but for the second picture here, this is accurate and imprecise. Why accurate? Because all the 4 bullets close to our target. But imprecise because of all the 4 bullets not close to each other. Okay, and for the third figure, this is inaccurate and also imprecise. Why inaccurate? Because all the 4 bullets is not close to our target. And also it is imprecise because all the 4 bullets not close to each other. So this is the first bullet, this is the second bullet, third bullet, 4 bullet. Okay, where they are not close to each other. And for the last figure, they are inaccurate but they are precise. Why inaccurate? Because they are not close to our target, but precise. Why precise? Because all the 4 bullets close to each other. Okay, so there are relationship between exact value and approximate value. So what is the relationship? So how to get true value? True value is approximate value plus numerical error. So we rearrange this equation. Okay, so to get numerical error is true value minus approximate value. Okay, so this is how we calculate error. And then we also must know how to calculate true percent relative error and also approximate percent relative error. So the first formula is about true percent relative error where the notation is epsilon t. So the formula is, okay, modulus true value minus approximate value divided by true value multiplied with 100. While for the second formula, okay, approximate percent relative error, the notation is epsilon A. So the formula is present value minus previous value divided by present value multiplied with 100. So what is the difference between true percent relative error and also approximate percent relative error? So true percent relative error, we are going to calculate the percentage between true value and approximate value. While for approximate percent relative error, we are going to find the percentage between present value that we get with the previous value. Okay. In numerical method, okay, most of the calculation is in iterative process, okay, where the computation is repeated. So when we are going to stop our calculation, okay, so there is a condition. What is the condition? Condition, if the given condition is epsilon A less than epsilon S, okay, where epsilon S is a pre-specified percent tolerance. And if this condition hold, that means acceptable result has been reached and no more iteration is required. And the second one, okay, if this condition hold, that means the numerical result is assumed to be within the pre-specified acceptable level. Okay, so for better understanding, so let's go to the example. Okay, a civil engineer has measured the height of 15 floor building as 394 meter and the working height of each beam as 35 meter. And actually, the true values are 3945 meter and 40 meter respectively. So now let's calculate their true error and true percent relative error. Okay, so let's come out with all the information that we have. So for engineer, okay, the engineer measured the building as a 3940 meter and also 35 meter. Okay, while the true value, okay, true value is 3945 meter and 40 meter respectively. And this will become our approximate value. Okay, this is approximate value. And this is our true value. So what is the error? So how to calculate error? Okay, so error is equal to true value minus with approximate value. Okay, so for height of the building, okay, for height of the building, so the true value is 3945 meter. And for the approximate value that the engineer measure is 3940 meter. So what is the error? The error is 5 meter. Okay, so from here also we can calculate true percent relative error. So how to calculate true percent relative error? Okay, so the notation is epsilon t. The formula is modulus, okay, true value minus approximate value divided by true value multiply with 100%. So true value minus approximate value. So we already have here 5 meter. Divide by, okay, we divide by true percent relative, true value. True value is 3945. Okay, and multiply with 100. Okay, so the percentage we have 0.13%. Okay, so now let's continue. Okay, to calculate error for height of the beam. Okay, by using the same formula, so error is equal to true value minus approximate value. So true value for height of the beam is equal to 40. Okay, while the approximate value for height of the beam is 35. Okay, so the difference between true value and approximate value is 5. And then we also can calculate, true percent relative error, epsilon t, where the formula is true value minus approximate value divided by true value multiplied with 100. Okay, and we already have a value for this part. Okay, so 5 meter divided by true value is 40 meter. Okay, multiply with 100. So the percentage is 30%. Let's say I add another information. Okay, let's say I add another information. Okay, previously, let's say we have first engineer. Okay, first engineer, measure the height of the building. Okay, height of the building is 3940 meter. Okay, and then 5 minutes later, we have the second engineer. Okay, calculate, measure the height of the building. Okay, building is equal to 3947 meter. Okay, so these two value is an approximate value. Okay, not a true value. So from the information we have here, actually we can calculate, approximate value, percentage error, epsilon A. We can calculate epsilon A. So where the formula for epsilon A is equal to present value minus previous value divided by present value multiply with 100. Okay, so present value. Okay, the second engineer 3947 minus with previous value the first engineer 3940 divide by present value 3947 multiply with 100. So epsilon A we get 0.18%. Okay, so I hope everybody can understand, how to calculate the error, how to calculate epsilon T and also epsilon A, and you can see the difference. Okay, what is epsilon T and what is epsilon A. Now let's go to the introduction of Taylor series expansion. So what is a Taylor series? Okay, Taylor series is used to approximate the value of the known function, and the function is represented by a sum of convergent series. Okay, so it depends how many terms you use to approximate the function. Okay, so if you have a few terms only, so the solution that you get is maybe far from the true value. But if you use many terms, that means the approximate value is close to our true value. Taylor series expansion of function is used extensively in deriving numerical methods. So, this is the formula for Taylor series expansion. Okay, so if you see from the formula, they have infinity term. So this is the first term, second term, third term, fourth term until infinity term. Okay, so this is the thing that I mentioned earlier. Okay, so if you want to approximate some function, and if you only use a few terms only, let's say you just use two terms, that means the answer that you get, is far from the true value. But if you use many terms, let's say until 7 term, 10 term, until infinity term, that means the answer that you get, you will get close to our true value. Okay, and then expansion of the Taylor series around x not equal to 0 is called Maclaurin series. And this is the example, okay, about a Taylor series function of fx. Okay, you can approximate for function exponent, cos x, sin x, and any other function. Okay, so we go to the example how to solve a function using Taylor series expansion. So example 2, approximate the function fx cos x using Taylor series expansion about x equal to 0 using 2, 4, and 6 terms. And then calculate the function at x is equal to pi over 12 and pi over 3. Okay. So this is the formula for Taylor series expansion. Start from first term, second term, third term until infinity term. And the question asks you to solve by using two terms, fourth term, and sixth term. Okay, so for the first step, okay, let's differentiate our function cos x. Okay, so y equal to cos x. Differentiate for the first time, you will have minus sin x. For the second time, minus cos x until, okay, the 5 times, okay, you differentiate. And then substitute the value x here with x is equal to 0. This one given. Okay, so when cos 0 equal to 1, minus sin 0, 0, minus cos 0 is equal to minus 1. Until minus sin 0, you have 0. So after you have this one, you just need to substitute into our formula of Taylor series expansion. Okay, for the first term, fx naught. So fx naught is equal to 1, so dia 1. For second term, f prime is equal to 0, 0. And then x here. And then for the third term, okay, this one, half, half, and then x square, x not equal to 0, so x square here. And then for the third term, f double prime is equal to minus 1. That's why you have x square over 2 factorial minus 1. Okay, you just substitute until you have the sixth term. First, second, third, fourth, fifth, and sixth term. So this is the equation, right? Okay, after that, okay, so let's approximate cos pi over 12 and also cos pi over 3 by using Taylor series expansion here. Okay, and then for the first one, okay, the question asks you to solve for two terms only. Two terms, that mean the first term and second term. So for pi over 12, okay, for first and second term, 1 plus 0 equal to 1. And for pi over 3, for two terms only, the same thing, 1 plus 0, so equal to 1. And then, if you solve by using fourth term that means first term, second term, third term, fourth term. Okay, so for cos pi over 12, okay, you just substitute into the fourth term, so you will have this value. And same goes to cos pi over 3. Okay, you substitute until fourth term, 1, 2, 3, fourth term. Okay, so you will have 0.4516. Okay, and the same thing, okay, you solve for using the sixth term. Okay, that means you need to use all the Taylor series expansion here. Substitute pi over 12 and also pi over 3. So this is the answer. Okay, so now we go to the truncation error. So what is a truncation error? Truncation error resulting from the truncation of the numerical process, and it arises due to the approximation method is used instead of the exact procedure. So previous example, example 2 about Taylor series expansion where we are going to approximate cos. Okay, that is a truncation error happen. Okay, so this is the example. So if I use two terms only, that means I truncate from six term, I use two term. Okay, that's happened. The truncation error happen. Okay, same goes to the fourth term, sixth term. Okay, as example, the numerical evaluation of cost function by using Taylor series is terminated after a certain term. Okay, so these contribute to the truncation error. Now we go to the introduction of round-off error. Okay, so number, for example, 1 over 3, exponent pi, okay, cannot be expressed by a fixed number of significant figures. Therefore, they cannot be represented exactly by the computer and must be run off. There are two situations in numerical computation when number can be shortened and lead to run-off errors, which is either by chopping or by rounding. And for your information, run-off error can be reduced by increasing the number of significant figures. Okay, for example, 2 over 3 is equal to 0. Okay, 2 over 3 is equal to 0.66666666666. Okay, and if you chop off the number, that means you just have 0.6666. And if you round off the number, that means you will have 0.6667. So that is the difference, okay, between chop off and round off. And lastly, is about total numerical error. So it's very simple. Total numerical error is a round off error plus with truncation error. So you will have total numerical error. So that's all about chapter 1, Introduction to Numerical Methods. I hope everybody can understand. Okay, you must know about error, how to calculate error, and then you must know how to do the Taylor series expansion, and lastly, you must know what about truncation error, about round-off error, and what is a total numerical error. Okay, so thank you guys.